All right. Good afternoon, everyone. My name is Bram Grooten. I'm a postdoc at the TU Eindhoven, and I'll be presenting this paper that was done during my internship at Sony AI. So let's dive in. So Sony AI a few years ago published this great paper where they show that they can outperform the champion Gran Turismo drivers with a deep reinforcement learning algorithm. And this was really impressive work. But it was only trained on one car and one track combination. So to deploy this RL agent in the game, they needed to generalize, because otherwise having 500 cars in the game and like about 100 tracks gives 50,000 combinations that you would need to save a policy for. And this is just too much. This would blow up the gigabyte size of the game. So we need to generalize. And to go into this direction, we took inspiration from a paper called RMA, Rapid Motor Adaptation, and it was designed for quadrupeds originally, so robots that can walk across many different terrains. And what they would do is you train a policy on many different domains, so you do domain randomization, and while you do this in simulation, you have exact access to the context that you're training on. So you can see the type of friction that you're using, the terrain height, and you can give this information to the agent. However, at deployment, at test time, when you do this in the real world, you don't know a priori what the friction is going to be. So we want a policy that can make use of this environment context during training time, but then not need it at test time. So what do? We have two different policies. We have the expert policy that does use the observation and the context. And in our case, for the car racing, this context describes exactly what type of car are you driving. So what's the mass of the car, what's the length of the car, the power of the engine, radius of the wheels. There's like 40 or 50 different features that we pass to this expert policy. And it just sees the observation, like the velocity that it's currently having and things like that. And it learns with regular reinforcement learning algorithms like soft actor critic on how to perform. But we cannot deploy this because it needs the context. So we have the adapter policy. And instead of the context, the adapter policy takes in a history. And this history consists of previous observations and actions for a certain window. So capital H number of observations and actions. In our paper, we used 50. We do some analysis on how many is the optimal, and 50 seems to be the right way to not waste too much compute, but still get the right performance. And what this history adapter is trying to do is it's trying to match the same encoding as the context encoder. So the context encoder is learning to really recognize what type of car are we driving, and then the history adapter is trying to match that. So it's really just doing supervised learning, trying to output the same z hat as the context encoder is outputting z. And that's with this, just a simple mean squared error loss. And the observation encoder and decision layers of the adapter policy are not in green because those are not learned, actually. They are just really the same weights as the expert policy uses. And this gives a strong final product. So the adapter policy is our final product that we test at deployment. So let me describe the experimental setup first. What we do, there's about 500 different cars in the game. So we sort all of them by using the car features by how normal or strange they are. So if they're very heavy or very light, like this racing cart, or very fast, then we leave them for out of distribution testing. And on the 80% most normal cars, so to say, we train on, so that we can really test the extrapolation ability of our algorithm. We do this on 3 different tracks. Grand Valley is a pretty standard one. Nürburgring is a very long one, so it's hard to really memorize. It takes about 6 minutes to really complete. Catalonia Rallycross is a very short racetrack, but it has some interesting context on the track as well, where the ground is changing from dirt to tarmac and back. So first, I'm show you some qualitative results. So these are out of distribution cars that the algorithms are not trained on. And you'll see that the baseline starts to struggle with having some weird movements all of a sudden, crashing into the side, or really wiggling a lot with this racing carts that is hard to control because it has it's very reactive, so you need to drive it very carefully. And you see that SPARC is able to recognize this context that it's either driving a very heavy car or a very light one, and is able to drive much more smoothly and actually complete laps with these unseen cars. So this is our main result. Also, so we mainly check two metrics. The most important one, I would say, is on the vertical axis. How many cars of this out of distribution set were you actually able to complete laps with? And you see that SPARC is able to complete it with more than 98% of the out of distribution cars. But it's not only completing them, it's also doing that very fast. So it has the lowest average normalized lap time. And then a little bit of an analysis. This is a more controlled experiment, I would say. So instead of generalizing across all of the cars, here we take one car, but we are able to adjust the mass and the power of this car. So we train only within the dashed square. So the default value we call 100%, and we increase and decrease that by 25% in the training phase. But then we test on double that range, so increasing the power or the mass by 50% or decreasing it. And you see that the fastest lap times are, of course, where the cars have the most power and the least amount of mass, because those can really go really fast. But those are also really hard to control. You can imagine that those cars can spin out of the turn really easily. And that is indeed what happens for RMA, the strongest baseline that we had. It crashed. The black squares show that it crashed in 8 of the settings. But SPARC was only crashing in one setting and was robustly able to finish laps in all of the other settings. And then one more experiment that I'd like to show you here. There's more in the paper, but Gran Turismo 7 is unfortunately a closed source game. It's a commercial PlayStation game. But so I really wanted to include some open source environments as well, so that researchers like you guys can continue on this work. And so we have some Majoko environments that I added some context to, and the context is now the wind speed. So the wind can go in the X direction and in the Z direction. And we want to see, can this one policy learn different behaviors, like walking into the wind or using the tailwind to walk faster. And also here you see that it has learned to lean into the headwind or make use of the tailwind to make bigger jumps. All right, thank you very much. I wanted to invite you to the poster, but that already happened. But if people still want to discuss, we can walk over there in the coffee break. Thanks.
Thank you for the talk. Very nice presentation. I have some questions. So actually, your expert policy is a very strong multitask learning algorithm, right? And so how did you deal with negative transfer issue for multitask learning? Like you have different contexts, and how did you ensure that the algorithm can learn well from all these different contexts and learn from one task will not lead to worse performance in another task?
Yeah, that's a good question. We did not need to pay a lot of attention to that, actually. So this was not a big problem, I would say. We just made sure that we uniformly sample across all the different contexts that we have. If you make sure that you have seen enough samples of each of the different contexts that you can face, then this will be all right. There are smarter ways where you might say, like, if I'm really struggling with one particular context or type of car, for example, you could sample that car more to see that more during training. But we didn't need to do that in this work.
So do you think it takes a lot of samples to train this universal policy for different tasks? And do you think there can be some improvement for the sample efficiency here?
Yeah, so like many RL works, the efficiency is not great in this work. Sony AI really just uses their actual PlayStation game to collect rollouts. We roll out on like 20 PlayStations at the same time, and we only need one GPU to train on all of that experience. But it does take a few days up to a week to train this policy, and it would be much better, of course, to iterate faster. Thanks.
Any more questions? In what you tried, did you see situations where the observation action history was not a good surrogate for the context?
Yeah, maybe in some settings where we tried a much shorter history, then it definitely is not able to catch like what type of context it's driving in. But once you have a long enough history of 50 steps, seems to be the right amount to be able to infer this context. And you can go further to like 100 steps, but that is just wasting compute at that point. You get the same performance. The terrain, no, yeah, we only do on one track at a time, yeah.
So the next author, please set up your presentation. We have time for one more quick question.
Hello, thank you for this insightful work. If I understand correctly, and please keep me honest here, you're tackling a partially observable Markov decision process where you're trying to infer the context. It's basically the belief, right? Belief state. So what are the necessary conditions that you need to have in the observation vector to be able to infer the state, so infer the context from the observations? That's the first question. And did you try to use an LSTM instead of stacking historical observations?
That's a good questions. So first of all, I agree that you would need to have sufficient information. You need some sufficient information in your observation to be able to infer some context from that if you have multiple of them. We didn't try LSTMs. That's a good idea. Then you can somehow use the whole history in a condensed way. So we use conv1d layers, like we use a convolution across just the time dimension. And yeah, that was simple enough and it worked well. Thanks.
Out of time now. Let's thank the speaker again.